Remembering back to our diagram, we want to be able to understand how the fish populations are changing over time. The reason is to assess if fish stocks are going up or down, and to see how healthy the stock is now compared with the past. Ideally, we'd know each year how many fish were in the water, but obviously that's impossible. Fortunately, we have another way of tracking changes in fish populations, and it relies totally on fishermen. The measure is catch per unit effort, better known as CPUE or catch rates. In this section, we'll examine how catch rates are calculated and how scientists take into account the factors that cause differences in catch rates, such as boats and locations. Most fisheries use logbooks to report what gear was used, how much fish was caught, and how much fishing effort it took for the fishermen to catch those fish. Combining this information together gives us a catch rate.
You might get 1/4 kilo a pot in the summer, probably 3/4 kilo a pot lift, something like that. Yeah, it depends a lot, every day is different, but that'd be a good average, I'd say.
Let's use Frosty as our example and show how catch rates are calculated. During this trip, he checked 50 pots and caught 15 kilograms of southern rock lobster. To get the catch rate, scientists simply divide 15 kilograms by 50 pot lifts and get 0.3 kilograms per pot lift. If there was more southern rock lobster around and Frosty had caught 50 kilograms for the 50 pot lifts, the catch rate would be 1 kilogram per pot lift. If there was less fish around, catch rates would be lower, and if there were no fish around, obviously the catch rate would be 0. Sometimes it's not just the amount of gear you set, but also how long you set it for that's important for catch rates. For Frosty's gill net, for example, you'd expect that he'd be leaving it for a few hours rather than 30 minutes. In this case, both gear length and amount of time are multiplied together to measure effort, called kilometre hours. Gill net catch rates are measured that way. If a fisherman caught 500 kilograms of shark from 4 kilometres of net soaked for 5 hours, his catch rate would be 500 kilograms divided by 4 kilometres divided by 5 hours, which turns out to be 25 kilograms per kilometre hour. Now, if you set the same amount of gear in an area where there are lots of fish, you will get higher catches than if you set the exact same gear in an area where there are not many fish. In this way, catch rates can be related to the amount of fish in the area where you set your gear. This is a really important concept for fisheries science because it means that catch rates can give you some indication of abundance. So let's spend some time going through this now. Here's an example of how catch rates can reflect abundance. We've put 200 goldfish in a tank, and here's our trawl net. What we're going to do is look at how catch rates change as the population decreases. So, our fisherman takes his first shot. Counting them out, he got 19 fish in the first shot. Speeding things up a bit, he's now taken 4 shots and caught 50 fish. He's now reduced the population to 150 fish, which is 75% of the original population. Catch rates have been pretty high so far. Let's get the fishermen to keep fishing and see if catch rates change. Now, the population is down to 60% of its original level, and you can see it's getting harder to catch fish. Catch rates have dropped right off. This example demonstrates that catch rates can provide some index of abundance. This is pretty simple, right? Not in real life. As you'd expect, catch rates don't only change with fish population size, but, among other things, with fishermen, gear types, seasons and depths fished. All of these things need to be accounted for. This is called catch rate standardization. And to show you how this works, we'll compare our first fisherman with a new entrant. Our first fisherman has been in the industry a long time and had pretty good catch rates. His gear is set up right and he knows just the right speed to tow. Let's see how the crazy scientist does. It looks like his gear isn't as good and his tow speed is much slower. Eventually he does catch the same amount of fish as the fisherman, but it takes him twice as long. So the crazy scientist ends up with less than half the catch rate. Now, it's obvious that comparing catch rates between fishermen won't tell us anything useful about population size or changes in population size. So what we need to do is compare catch rates of the same fishermen over different years. So let's get them both back onto the fishing ground. Because the population had decreased, both fishermen have lower catch rates. If we do the maths on this, what we discover is that although their catch rates are very different, they have both experienced the same fall in relative catch rates. In each case, they both experienced about a 50% drop in catch rate. The next step is to standardise the results, which means to even out the differences between high catch rates of one fisherman and low catch rates of another. Going back to our fish tank results, in the first year our fisherman had a catch rate of 7 fish per shot, and the crazy scientist had a catch rate of 4 fish per shot. In the second year, abundance has fallen, so our fisherman only had a catch rate of 3.5 fish per shot, and the crazy scientist only 2 fish per shot. We know that the major reason for the catch rate difference was that the crazy scientist had a smaller net, and scientists need to even out the differences caused by the different nets to make the results comparable. Remember, we're not interested in the comparison between fishermen, but the comparison between years, so we can understand changes in abundance. The process of standardisation then means that in our fish tank example, we want to make the first year's catch rates the same. In this case, we'll use round numbers and make the first year's catch rate 1. To achieve this, we divide the first fisherman's catch rate by 7 and the crazy scientist's catch rate by 4. Now going to the second year, we do the same thing. Divide our fisherman's catch rate by 7 and the crazy scientist by 4. What we've done here is standardised both their catch rates and therefore adjusted for the fact the crazy scientist had a smaller net. Result? Even though the catch rates were very different, by standardising them we can clearly see that the changes in catch rates were the same. The catch rates could now be combined to get an average catch rate for the fishery for each year. Applying this process to a commercial fishery is exactly the same, but over a much larger number of fishermen and more variables. Those variables being things like gear type, depth, season and area. Looking at standardised catch rates over a number of years, scientists can tell if a fish stock is going up or down. The large number of logbook records provided each year across a whole fishery helps to show the bigger picture that might be hard to see in the catch rates of any one fisherman.
I record where we fish, basically how much gear I use, the bycatch, all the bycatch species, anything we discard, whether it's alive or not, any interactions there might possibly be, which is extremely rare again.
Now, scientists acknowledge that using catch rates to measure changes in fish populations isn't perfect, because there are just so many factors involved, many of which can't be measured. Examples of variables that are difficult to account for are market price and quota availability. But for many fisheries, it's the best information available. To get a more accurate measure of changes in fish populations, scientists sometimes use fishery independent surveys. These surveys use standardised gear and trawling methods and are designed to take out many of the factors that might cause unaccounted variability in catch rate calculations. We'll look at them in more detail in the next section. In summary, what we've looked at in this section is how catch rates are measured and the process of using catch rates to estimate changes in abundance of fish populations. A really important point to remember from this section is that the accuracy of catch and effort information from fishermen greatly affects scientists' abilities to be able to monitor population changes of fish stocks. In our next section, we'll be looking at the process of how scientists collect data for stock assessments.